Alright, so this video will be about quantum mechanics with Python, and in particular in this video we look at particle in a box model and the energy levels and wave functions of this particle in a box. And this is one of the first example quantum mechanics systems, a very simple system that you see, but which already displays some important quantum mechanical properties that we will look at. And here I've just plotted for so that it's nice to see this box in which the particle is in, or an infinite square well. And here you see some of the first probability densities resulting from the wave functions of the different energy levels. But we'll be looking at those in more detail. So let's begin. First, here I've just defined some or imported some libraries, Python libraries that we will be using for this particle in a box system. So very standard NumPy, pyplot, and also this animation function or animation class from Matplotlib. And then also just to show the animations in this Jupyter notebook, it's good to have this IPython display. And then I use some pyplot default styles for the plots so that they look nicer. For example, I define that the line width will always be 2.5 and so on. So this is just cosmetics for the plots. Then the plan for this video, which will be the first part of this particle in a box series or two-part video, like I said, we will here look at the energy levels and wave functions of this system. And the plan is that we always have to start by finding the Hamiltonian operator which defines your quantum system. So each different quantum system will be described by a different Hamiltonian operator, and then depending on what is the Hamiltonian, the wave functions will look different. So once we have found the Hamiltonian operator, then we have to solve the time-independent Schrödinger equation, or you can equivalently say that you need to find the eigenfunctions psi n and eigenvalues or eigenenergies actually En of this Hamiltonian, and it looks like this. So it is a standard eigenvalue equation that you have to solve, and once you have done this, you get to do physics. And for example, plot the wave functions or energies or so on. And in the second part, we will look at the time evolution of this system, but I will not go into details what we do there, but that will be for the second part. So we begin by finding the Hamiltonian operator, and in general, the Hamiltonian can always be written like this. As people who have studied basic quantum mechanics will know, it's a differential operator, and this particle in a box quantum mechanical model is defined so that this potential energy described by V is 0 if the particle is inside the box, which is located, the left corner is at the origin, and then the right corner is at L. So it's a box of width L. And like I said, inside the box, the potential energy is 0, and it's infinite elsewhere or outside the box. And that means that the particle cannot exist outside the box. And that is what defines this particle in a box model. So our Hamiltonian inside the box is simply just this, essentially this second order derivative with respect to x. And then we move on to solving the Schrödinger equation for this system. So now we just use this Hamiltonian that describes the particle in a box in this Schrödinger equation. And now here I've just plugged everything in and rewritten it like this. So it clearly now looks like a pretty simple differential equation. And here I have denoted with this Kn just all the constants that appear, so it's more convenient to solve. And you can recognize that this here is the differential equation for simple harmonic motion. And it has a general solution that looks like this. You get it from standard differential equation or ways of solving differential equations. But then to determine these constants a and b that appear in front of the sine and cosine functions, um, you have to know the boundary conditions. And in our case, of course, the boundary conditions is at the corners, the wave function has to equal 0 because we know that the particle cannot exist at the corners or outside the box. So we have to have, or we require that the wave function is equal to 0 at those points. So from this first condition where psi n at the left corner or at 0 equals 0, we get that this b has to equal 0, which gives us this kind of wave function. So we only now retain the sine part. And from the other end, so when the particle is at the right end of the box at L, it also has to, or the wave function also has to equal 0 there. And the only possible non-zero solutions for this wave function to be 0 is that this kn has some particular value which enters this sine function. And actually here we see that for this sine to be 0, there has to be some kind of integer entering to the value of this k. And here we are only interested in values of n which are 1, 2, 3, and so on, for that there is a particle in this case, because n equals 0 would mean the trivial 0 solution, and we don't want that. So n is an integer starting from 1 and then goes to 2 and 3 and so on. So now our wave function looks like this. We have plugged in the k value, and then in the end, because we defined k here above, we defined it to just include all the constants that appeared in the problem. You can solve for the energy. And now we see that, like I've written here, that since this integer n enters the value of energy, we see that the energy is quantized, like the ones of you who have done this before know that this is what you get. Which is nice to see. It really arises from the boundary conditions of the problem. But then we also need the constant a, and that we get from the normalization requirement. So we require that the particle, or sorry, the probability density, which is represented by this product, integrated over all space, has to equal 1. And just from that requirement, you can solve it, and you get that a is this square root expression. So now we have essentially solved the particle in a box, or this one-dimensional particle in a box problem. And here I've just collected our essential features of the problem. So the wave function looks like this, and the energies look like this. And now we can start coding and looking at or plotting these wave functions and so on, and looking what happens. All right. So first of all, I will just note that I'm using energy units where h bar squared divided by m equals 1. It's just a much more convenient way to do these plots, because h bar squared is a really small number, and I don't want that. So this is just some fancy energy units, but that's not so important. So here I simply, with standard Python function definitions, I define this energy expression here. Then I also define the wave function, which is given here. And in the end, I also have a different function for the probability density, which is just this wave function, or the absolute value of this wave function here squared. So it's convenient to define functions for these different things that we will be plotting. So we begin from the energy levels. I will first plot the first 5 energy levels as a function of L, which is the length of the box. And here, first I've set L to go from 1 to 3 with evenly 100 evenly spaced values. So that's an array from 1 to 3 with 100 values. And this ends go from 1 to 5 actually. That's how this np's arrange function works. So I have integers from 1 to 5 here. Then I just create with pyplot, I create this figure and axis for the plot. I go through a simple loop where I loop over each n, which corresponds to the energy levels, and I plot the corresponding energy as a function of L and put a label for that specific plot or specific curve so that we can see it in the plot. And then I add some cosmetics for the plot. And you can look this in more detail by pausing the video. So here it is this the result of the plot, which looks quite nice. And the important features that you can see here is if we start from a small value of L, which is equal to 1, it means that the particle is more confined. And maybe you have heard that in quantum mechanics, usually the smaller the system, the more pronounced the quantum effects are. So here you can see that when we have a small box, these energy levels are really quantized, or there's a clear distinction between these energy levels, and there's a gap always between the consecutive energy levels. But once we start increasing the length of the box, which means we're increasing the system size, so to speak, these energy levels get closer and closer to each other, and this quantization starts to become less apparent, which means that these quantum effects get weaker, so to speak. So this is nice to see. Yes, and here I've written that quantum effects decrease as L increases, which is what we saw. And then we go to the wave functions. So I will plot the first 3 wave functions for the particle in a box with L equals 1. So that would be this first plot here corresponding to L equals 1. And again, very similarly, I define L equals 1. X-axis goes from 0 to L with 1,000 values. And here I have the first 3 energy levels as an ends array. Again, I create the plot with biplot subplots. I loop over the different energy levels and plot these corresponding wave functions here. And then I just add some cosmetics to the plot. And I also actually add the potential energy, like this the square well, or this box in which the particle is in. So it's nice to see. All right. So here's the result. You see the first 3 energy levels here. So if we look at the first energy level, you see that there is it's like a clear just one kind of looks like a parabola in some sense, and there's a higher value of the wave function in the middle, and then as we go towards the edges of the box, the wave function goes to 0, which is what we required by the boundary conditions. And there's no value at all for the wave function outside the box, which makes sense. That's what we want. And once you go higher in energy, so going from psi1 to psi2, you see that 2 things appear. So this wave function starts to get more curved, and curvature of the wave function is always a measure of the kinetic energy in the system, or the momentum in the system. So once you increase energy, go up in energy levels, the kinetic energy in the system increases. And this is seen by the curvature of the wave function. And also these nodes start to appear. So for the second energy level, there's one node in which the wave function passes 0. So that will mean that the particle will never exist in this area because the wave function is equal to 0 there. And for the third energy level, you again see that the curvature increases. So you go up in energy, and the particle gets more kinetic energy or more momentum. And we also get an additional node. So now there's 2 places where the particle will never exist. So it's nice to plot these different wave functions and see what happens. And then that's only the wave function. So I will do the same thing for the probability densities, which I remind is the absolute value of the wave function squared. So similarly, I create the figure and the axis for the plot. I loop over different energy levels and plot the probability densities. Then I add some cosmetics again, add the potential energy as these black lines and so on. And again, here's the result. So it looks quite similar as the wave functions, but now we of course now we of course see that the wave function does not go to zero, or the probability density does not go to zero because, does not get negative values. Importantly, it does go to zero, but doesn't get negative values because probabilities always have to be positive. So we see that these nodes still exist for these higher energy levels. There are places where the particle will never be found, here, here, and here. And there are also some peaks with highest probability for these different energy levels where the particle is most likely to be found. And this is nice to see. And then the last thing I'm going to plot, or actually do an animation on, is when we change this size of the box and what happens to the wave functions when you change L or change the size of the box. And here I plot the first 3 wave functions when this L goes from 1 to 5, or I think it was actually one from, yes, here from 1 to 8, but anyway, I forgot to change that. So we again create the plot, and here I have defined an update function, and this corresponds to each frame in the animation. So this does one plot to this figure and axis, and it's always it takes as input this L value, or the length of the box, which means that for each L we do 1 frame in the animation. So, and when those frames are shown one after each other very quickly, you of course see a movie of the system. And here are just some calls that do the animation with this matplotlib library. And here I've shown the animation in the Jupyter notebook. So this is the result, and first I'm going to play it once so we see what happens. Yes, let's go to the start again, and you really see that once you increase the length of the box from 1 to 8, something really happens. And I think in this Jupyter notebook or in this IPython display window, you can, with your mouse, you can move this or see different frames quite interactively, and this is very nice. So if we start from, let's say we start from a long box of L equals 8, and here you can see that because now we don't have so much information where the particle might be, because it's quite a big box, so we have less information or less certainty about where the particle will be. That means that we kind of have more certainty about the momentum in the system, and this means that there won't be so large values of momentum or large values of kinetic energy in the system. And that's seen here because this wave function, the curvature gets less and less pronounced as we increase the size of the box. And once we start once we start decreasing the size of the box, you see that this curvature of the wave functions starts to increase. So I will show it again, going from 8 to 1. You see that really this curvature gets more and more pronounced. And this is actually, like I was explaining and I've written here, this is a manifestation of the Heisenberg uncertainty principle, which is built into these into the Hamiltonian operator actually. So now that we have decreased the size of the box, we have more and more information or more and more certainty where the particle will reside, but that we have and that has a so to speak has a cost, which is the uncertainty in the momentum of the particle. So now we will see that there has to appear also high values or higher and higher values of momentum or kinetic energy when we decrease the size of the system, and this is seen by the increase in the curvature of the wave function, which, like I said, measures the kinetic energy in the system. So a large box means you have less information where the particle is, but probably more information, or likely more information, about the momentum in the system. But then a small box will mean that you have more information where the particle will be, but that inevitably leads to the fact that you have less information about the momentum. So there has to be high values of momentum also, or higher values of momentum in the system seen in the curvature of the wave function. So here we have shown some very standard plots, very standard ways to study this particle in a box system, and in the next video we will look at time evolution in this system and how these different wave functions can mix together and what happens as time evolves. Okay, so thank you for watching.